Lecture 15, S-Parameters and the Scattering Matrix. While Z and Y parameters, the reactance and admittance parameters, can be useful description for network, S and ABCD parameters are even more widely used in the microwave circuit. As we'll see shortly in this course, S parameters play a hugely important role in microwave engineering. Consider again the multi-port network from the last lecture. Rather than focusing on the total voltage and also currents, which is the sum of the positive and negative waves at the terminal planes, the S parameters, however, are formed from ratios of reflected and incident voltage wave amplitudes. When the characteristic impedance of all the transmission lines connected to the network are the same, as in the case for the network shown above, then the S parameters can be defined as V1 minus up until Vn minus is equal to the S matrix S11 up until Snn times with V1 plus up until Vn plus. Or you can have it to be V minus is equal to S, the scattering matrix, times with V plus. In the last lecture, the terminal planes are phase equal to 0 at each port. So that's why you will have this equation. So for S parameters, each of the S parameter can be computed as S1j is equal to V1 minus over Vj plus. Notice that this expression, that the wave amplitude ratio is defined from port J to port I. Alright, please consider this figure over here. You have a two-port network. So you have port 1 with V1 plus and V1 minus. So V1 plus here indicates the incident voltage wave, and V1 minus is the reflected voltage wave. And then you have port 2 with V2 plus, the incident, and V2 minus, which is the reflected wave. Now, using equation 2, you will have S11 is equal to V1 minus over V1 plus, when your V2 plus is equal to 0. Right, why do we make the V2 plus is equal to 0? This is because, number 1, there is no source on the port 2 side of the network, meaning here, port 2 will be no source. Or number 2, port 2 is very well matched, so there will be no reflection at all from this port. Consequently, with V2 plus is equal to 0, your S11 will be equal to the reflection coefficient at port 1. Next, we're trying to find the S21. So S21 is equal to voltage at port 2 minus over voltage at port 1 plus, where your V2 plus is equal to 0. Again, with a matched load at port 2, so that your V2 plus is equal to 0, meaning that there is no reflection at all, then your ST1 would be equal to T21, which is the voltage transmission coefficient from port 1 to port 2. So S11 is actually a reflection coefficient only when your V2 plus is equal to 0. It has to fulfill the two criteria that we have said earlier, where it should be very well matched. Port 2 is very well matched, so there are no reflections from this port, or there is no source on the port 2 side of the network at all. Let us refer to this example. So you have a two-port network that have the following S matrix referring to some system impedance Z0. So here you have S is equal to 0.1 as your S11. Your S12 is 0.8 with a phase of 90 degree. Same with your S21, 0.8 with a phase of 90 degree. And your S22 is equal to 0.2. Now, if a short circuit is connected to port 2, what is the resulting return loss at port 1? So how do you find this? From the definition of equation 1, you will have V1 minus and V2 minus is equal to the S matrix, which is S11, S12, S21, and S22, times with V1 plus and V2 plus. So from this matrix, you will have an equation of V1 minus is equal to S11 times V1 plus S12 times V2 plus. So for V2 minus, you will have S21 times V1 plus S22 times V2 plus. So how can we incorporate the short circuit load into this equation? So remember the two conditions that we have earlier. So you have to make port 2 as short circuit. So here you have a short circuit at port 2. So from this circuit we see that the reflection load is equal to V2 plus over V2 minus. So your reflection load for a short circuit would be equal to -1, meaning that your V2 plus is equal to minus V2 minus. Now we are going to insert this equation into the previous equation before. So you will have V1 minus is equal to S11 V1 plus minus S12 V2 minus, and V2 minus is equal to S21 V1 plus. Plug in V2 plus is equal to minus V2 minus, then you will have minus S22 V2 minus. Now rearranging all this equation, finally you will have the reflection is equal to V1 minus over V1 plus, which is equal to S11 minus S12 S21 over 1 plus S22. So this will be the input reflection coefficient expression for a two-port terminated in a short circuit. So just plug in all those values with the S11, S12, S21, and S22. Then you will have your reflection coefficient is equal to 0.63 and your return loss will be 3.97 dB. Let us continue with lecture 16, the properties of S matrices and the shifting of reference plane. For reciprocal networks and S matrices, it can be shown that S is equal to S transpose, where your ST indicates the transpose of S. So in other words, S is symmetric about the main diagonal, which is what we also observe for the Z and Y matrices. For a lossless network and S matrix, so the condition for a lossless network is a bit more obtuse for S matrices. So you will have a lossless network when your S conjugate is equal to the inverse of your S transpose. This result can be put into a different and possibly more useful form by pre-multiplying your equation 2 by S transpose. So here you have S conjugate is equal to the inverse of S transpose. Okay, so here you will have S transpose times with S conjugate. That would be S transpose times with the inverse of S transpose. Then that will give you I. So I is the unit matrix which is defined as 1, 0, 0, 0, and then you will have 0, 1, 0, 0, 0, 0, and then you have 0, 0, 1, 0, 0, up until 0, 0, 0, 0, 1. Okay, so expanding equation 3, we will obtain, so this part here is your S transpose, okay? This is ST, so S transpose. So you have S11, S21, up until SN1. This one goes until SNN. And then you have the S conjugate. Okay, this is S conjugate. So you will have S11 conjugate, S12 conjugate, up until S1n conjugate, down here up until SNN conjugate is equal to the unit matrix, the I matrix. Okay, so if you take row 1 times column 1, so that will give you S11 times S11 conjugate plus S21 times with S21 conjugate up until SN1 times with SN1 conjugate. That will give you 1. So generalizing this result, that will give you the summation of SKI times with SKI conjugate is equal to 1, where your I is equal to 1 up until N. So in other words, this result states that the dot product of any column of S with the conjugate of that same column equals to 1 for a lossless network. Now we take row 1 times with column 2. So you will have S11 times with S12 conjugate plus S21 times with S22 conjugate up until SN1 times with SN2 conjugate. That will give you 0. So generalizing these results, you will have the summation of SKI times SKJ conjugate is equal to 0. So in other words, this result states that the dot product of any column of S with the conjugate of another column will be equal to 0 for a lossless network. So this is how you find out whether the network is lossless or not.